Okay, so we can probably continue. So we've been through this rendering equation. I basically explain each part. I repeat this just to say that there's something called the rendering equation, and this is what we would like to approximate with some algorithm. Okay. Oops. Yeah. So that will be the theme of this talk. We basically answered. Yeah, I have to talk a little bit about some more things. I see. So this BRDF, this third function you see in there, this one, is basically only capable of taking into account reflections. So you have some incoming rays, you get some outgoing rays. It may be one or several reflections, and it depends, of course, on the normal vector of the surface and those sort of things. This is called bidirectional reflectance distribution function, basically how things bounces off in different angles. Now this one is only working if you have an opaque surface. So there's no light traveling through it or getting transmitted or absorbed. You have another function that will deal with these cases. So very briefly what that is. If you, for example, have water in the glass, light will basically shine through it. And it will come out at different angles due to refractions. Light comes into one medium, it changes speed, and therefore it's also changing its angle of incidence out from this media again. And basically three things can happen. You can get this reflection, you can get the absorption, which is basically that light disappears. For example, if you painted the wall in a particular way, you would absorb some of the light. And transmission, that it goes through in some way or another. And then again is depending on how photons are scattering inside your medium. Then you have other type of surfaces, like this statue shown here, that is appearingly glowing when it's lit up, and that's because you have a complex combination of many of these reflections and reflections inside of this one. This, for example, happens if you try to take a flashlight and light through your hand, you will see some light going through. It's basically the same thing. And you get this sort of dim, sort of lit up things where you have light coming through in certain places and it doesn't pass in other places, and so on and so forth. These are also quite complicated things. But to really get a realistic type of rendering, you should also have a function that is capable of taking these sort of effects into account, not just reflections. And in physics, you do that by introducing another function. This is the BRDF we saw in the rendering equation. This is another one. It's a little bit more complicated, but it takes into account that you may have light traveling into the medium, being reflected, and then coming back out. So it's just the BSSRDF, which stands for bidirectional scattering distribution function. Which is more complicated. I won't show it here, but if you put that into the rendering equation, you will also take these sort of things into account. Now the different techniques used to render is basically trying to take also that component into account to make some things look realistic. I think we already seen the problem with using this rendering equation. That, yeah. It's not recommendable to try to implement it and then think that your computer is going to run some fast graphical animations. So we have different ways of trying to approximate this. I won't go into very much detail on each and every one. Some of these can be implemented in OpenGL if you want to go further with graphics programming. Some of them are like a gold standard, which you use to compare your algorithms that you make yourself with. So the first part we'll talk about is more ideal approaches that gives you quite good rendering, and then towards the end I will talk about what we will basically deal with, which is a simplified model. So I don't know, you need, anyway, all these methods is a way of approximating the rendering equation in one way or another. We call them global because they take into account direct illumination plus light reflected off other surfaces, like in this room, for example. It's an interaction between the direct light source and things reflected off the walls. And you have basically four main techniques I'll talk about. One is called ray tracing. Anybody's heard about that? Yes. Heard about it? Know what it is? I don't know too much either, so I
Is there Microsoft is implementing this on its devices?
Yeah.
Some future games, something like that.
it's basically a way of rendering and trying to approximate this rendering equation. And I think you can also, you have implementation, I think, in the Super Bible, for example, that shows how you can do this in a simplified way. So artificially speaking, you're basically taking your camera and you're shooting rays in the opposite direction for each pixel. And this is to tell you what intensity and color you should put in each and every one pixel. So you're basically shooting it artificially into your object, and then it will bounce off whatever objects you have in there. And some will bounce off several times, eventually reaching the light source. Other will, come down into a area and then bump into the surface, basically not ever reaching the light source, telling you that that should be a shaded area, right? So, for example, this pixel here should be colored more darkly than, for example, the one here that's reflected back to the light.
So that's like doing the reverse of what light does.
Yeah.
Instead of accepting light, you're
the reverse, with one additional thing added, and that's the reason why they do it in this way. Can anybody imagine why you would send it from the camera and not just care about the light that's in the scene?
Because there might be light that you're not, that's not coming to the camera, so there's no point in.
Exactly. So it's very nice because now you only care about light that comes into your viewpoint, right?
Yeah.
That's why they basically do it this way. And if you look in a general room with several lightings, here I just put the screen here as this eye, basically. It's what you see. So it may bounce off, one time, then you have some intensity on that particular pixel. If it bounces several times, the pixel becomes a bit dimmer, for example. If it's going directly to the light source, of course, that should be a very light pixel. So basically, fragment shader work in a sense. But there's one problem with this one. Can anybody imagine what that may be?
Sorry?
There's a problem with this approach.
The second one?
Except for it being slow. It's of course slow because this is quite a demanding task to do. So this is an offline rendering technique. You basically use it to, make nice looking pictures, or maybe if you want to make a movie or something like that. But there's a problem with it and just shooting it in this way. It's basically hinted at in this particular drawing.
Shadows will always look the same.
Yes. Shadows will always look the same, and they will always be quite hard. It's very difficult to figure out soft shadows, and particularly shadows that comes from transparent objects, what you call caustics. In this case, if you have these different spheres here with different materials, some you can shine through, for example, it cannot cope with that situation at all. It will just hit the surface and say, no, there's nothing here, so I just put it into a darkened pixel instead of something that may be lit up. And I try to illustrate here by just putting a black surface on the ground here. And what happens when you don't see these things is that it looks a bit more artificial. It's not what you expect. Like this sphere number D here, you would expect it to have a very dark and hard shadow, but the sphere A and B, you would expect there to be some sort of light coming through, right? It should look natural. So to cope with these things, you use another, also quite computationally heavy rendering technique, where you simulate photons traveling from each light source in the room. And then there will be some places where it bounces off surfaces and hits, and the number of photons that will be gathered at one spot will depend on surface properties. Whether it's transparent, whether it absorbs, and those sort of things. So you do this first. You make a map out of where each photon is landing. That's why it's called a photon map. And then you have a second stage, which is a ray tracing going the other way around. So making these photon maps is something it's basically a simulation of how photons travel in space in physics, and then you put down your material properties and you make this map. It can be done quite efficiently, but this is also something you do offline, I think. I don't think you can do this real time at all. And of course, then you use ray tracing again. And then, of course, if this surface had been glass now, you would have photons traveling through it, and there will be gathered some photons here that will be discovered in a map. When you send the ray back, you'll discover there's something over there, and you will put that to a pixel that is something different than dark, for example. So you get the impression that light is shining through. So by first emitting these photons, making them bounce or get absorbed and transmitted depending on the materials in the room. Then using ray tracing, you get something that's quite nice, and you can deal with this situational caustics like you saw here. So to compare the two techniques, can you see which one of these is ray tracing and which one is photon mapping?
The first one is ray tracing because
The shadows.
the light isn't going through.
Yes, exactly. So you have dark side shadows, and this is how it would look with photon mapping. And
And also around the light, there's no.
yes, it's exactly, it's completely black. There is nothing reflected back either. So you see that ray tracing can cope, you know, it can look decent enough, but if you compare it to something where you really try to make it look realistic, you see it's looking quite artificial. So it's looking more realistic. Therefore, I mean, some are starting to go away from this ray tracing algorithm. You have also something called path tracing. It's basically a numerical solution to this rendering equation using something called Monte Carlo integration. Is that something anybody knows anything about?
Sorry?
Monte Carlo integration. I guess that's probably something you don't know. It's a way of solving an integral, basically.
The
And
Monte Carlo probability problem?
yes, it's related to that. So you're basically testing a lot of trials. Same thing you do when you try to make a weather prediction. You just try a lot of trials and you average. So here, in case you do it here, you have many rays per pixel, and you see how they bounce off different objects, and you take the average to figure out how you color your pixel, basically. And then you use this BRDF function to determine the illumination towards the viewpoint, to take out what will be seen or not. And these paths can have many bounces depending on the object in the room, and the more they bounce, the more you can assume that that's a dark area you're looking at, basically. It also is capable of keeping track of color information. So it's a very accurate one. It's making things look very physically realistic. Therefore, it's quite computationally heavy because, you know, if you put in 10 rays per pixel, you will have a lot of these noise artifacts. So you need a lot of these rays to be able to average out everything and make it look smooth. Here you have 100 ones, and then it starts to look quite decent. To make it converge, meaning that you will get the same result every time you run this, you need several thousands. So it's not a simple or a very computationally light algorithm either. But you could use it, since it's quite accurate, you can often use it if you have enough rays here to compare against other models. Because if you get close to this, it will be an indication that your model is quite good, right? But also if you want something to look very physically accurate when you render in certain times, if you want to have an animation of an object and you want to really study its physical properties, it's nice that you have something that can give you a physically realistic rendering. But for our purpose, this is way too complex. I say that these algorithms are out there and they're possible to implement, but we won't touch upon that in this course. Then we have two more. One is called radiosity. It's a bit simpler. In this case, you don't really care about reflections, specular reflections. You know what that is? When you're moving outside in the snow now, for example, in sunlight, you will see lots of sparkling, where light is more or less reflected directly. And if you have mirrors or surfaces that is, you know, this is a bit shiny, so some light is reflected. It's not completely specular, but it's not diffuse either, which they assume in this case. If you can assume diffuse surfaces, we can do a lot of simplification using this radiosity method. And it's basically working by subdividing your scene into different areas, you know, with geometric primitives, for example.
Is that the same thing that happens at water and sea?
Yes, exactly. That's specular. So if you don't have those phenomena, this radiosity is a simplified rendering algorithm that can do quite well. But if you have a lot of specular reflections, it doesn't really cope with it. But if you have a room of diffuse, and this is pretty diffuse. Most things in this room is pretty diffused, except for the screens on this computer. This blackboard is not, or whiteboard, it's not really diffuse. That window is not diffuse at all. But any other diffuse object will look quite nice in this way. So you can do certain simplifications, but I won't go into details of exactly what you do. But if you compare them, here you use this radiosity, and here you use 3 different light sources to make this room look more or less realistic. Using this radiosity in this room consisting of basically just diffuse surfaces, you can get a very realistic effect just by having one light source outside. So it's capable of doing realistic rendering, but under with diffuse objects. So that's the limitations. And before I start with these simplified methods, there's something called scanline rendering. It's not really a rendering technique of its own, but it's used in combination with other methods to sort of simplify your computation. So it's basically shown here that you draw lines through the image, and then you basically figure out by using this C buffer, which tells you what is in front of the other. If one object is including the other, you basically remove the part of the object that is occluded, and so on and so forth. And then you do this line by line by line, like this, scanning the whole thing downwards. And it will remove a lot of unnecessary computations. So it's just a method of removing some computational load. So I will not speak anything more about this if there's no particular interest in that. It's basically rendering techniques that are out there. They're quite accurate, so you can use them for this offline sort of rendering. And if you would like to make very professional rendering of certain scenes, or as I mentioned earlier, if you want to make a movie that looks realistic, you can do all of these things because you have all the time in the world to make each frame look nice, right? But in our case, it becomes too slow because we won't also look into real-time rendering. And then you have to use more mathematically simple models. Again, you like to approximate this nasty equation, this rendering equation, but you have to make some trade-offs. You have to make it look plausible and a bit natural, but it will not be particularly physically accurate. Then you can do a bit more simple things. The point is, if you want it to be real-time rendering, you have to simplify. They should be fast. They should be easy to store. And one of these models is called foam lighting model. So it's a good approximation, but it's not physically accurate. And it's basically consisting of 4 components. So today I will just go through what it is and how it approximates things. And I will use another hour probably before the lab we will have on this to explain how you code this thing. But now just to tell you what it's all about. So first and foremost, the light source itself is difficult to model. Usually you do some simplifications there. If you want to model this light bulb over there, for example, it's quite complex. But you could approximate it as a point with a sphere around it or something like that. So the simplified models of light is basically what is called ambient light, and we'll get back to that on the next slide. It's basically light everywhere that has no direction. It's basically just lifting your luminance of the whole scene without anything else. Everything is scaled in the same way. A little bit like, maybe not totally correct to say, but on a very cloudy day, we'll basically have something that's close to ambient light, but it's not completely, because you still have some shadow casting and those sort of things. But it's basically directionless light, just to add on to the luminance in your image. Then you have point lights, which are shown over there, and you have directional lights and spotlights. I'll just go through each and every one of those simplified models one by one. Ambient lights, basically called omnidirectional or fixed intensity or fixed color. Lowest level light everywhere, so all parts of the scene is just lifted with a sort of constant, basically. And the only thing that comes into play here is the surface property, which is this K ambient factor, and the intensity of the light source that you want to model. And then you just take the product of them. And it's the same intensity all over the room. So basically all you need is the physical property of that particular surface, how much it depending on the color and those sort of things of the surface, it will be brighter or darker. So you can differentiate those things. The ambient light doesn't need to be white. All objects will have the same intensity. And as we see here, things appear pretty flat. So call it background lighting, if you like. And it's very easy to code, but I won't get into details on that now. It's basically elevating everything with a constant. Point lights, then you have everything radiated from a point in 3D space, which will be basically symmetrical around the sphere. I've shown it here in 2 dimensions, so you have basically things radiating in all directions. It will look like that, a sharp point at the center, and I will just gradually dim the further you get away from it. If you put objects around them, it will always cast a shadow out from the center of this light source. So that's point light. And you often use that to, for example, mimic light bulbs in your scene. Directional light, usually strong light coming in one particular direction, like you see here on this side. The light is coming in from the left, going to the right, and you get all shadows cast in one direction. Anybody who can see what sort of light that may try to replicate?
Sun.
Yes, exactly. So
It
on a
has to be
sunny day.
something that's really far away, because technically everything radiates in a point-like fashion, so you would have to be very far away for it to be.
So the sun is actually a point light if you see it from the universe perspective, but for us it's basically a directional light. So it will cast light more or less in. Or was that what you, or did you mean something else?
Yeah, that's what.
Yeah. So you basically see it very well here, sunlight coming in from the side. You get these shadows cast like that. So point light and directional light, ambient light, and then the last one is spotlight, which is basically just a point light where you cut off at certain angle. So you have this point coming here, you know it would radiate in all direction, but you just remove a certain angle of it, and then let it just radiate within some sort of angle, and then you get a spotlight. So quite simple to model all of this. And with all these four light sources, you could basically do quite a lot. Yeah. So to the different components in the fun model, how things are bouncing off surfaces. Now we already talked about ambient light. It's just making something stick out from black. So here you see very good what an ambient light means. It makes things look entirely flat, but it just lifts the luminance of the object a little bit. Then the additional one is the diffuse reflection, specular reflection, and the sum of them is called fun reflection, basically. And by this plus emission, if the surface also emits light at the same time, will make your object look quite decent, actually. So ambient, we already seen. Diffuse is basically angle, depending on the angle of incidence of the incoming light wave, but it's scattered evenly in all directions. Specular is like this snowy sheet showed you. You have this sparkling effect that you will see at certain angles, and if you move a little bit away, these sparkles may disappear, and other sparkles may appear, and so on and so forth. Often, if you look at a car in sunshine, you will see these specular reflections. And then, of course, the emission. All added together is the fun model. This is what we will basically consider a lot, at least in the beginning. Any questions to this? Okay, it's okay. Yet just another way of trying to approximate the rendering equation. Has many of the same components, right? Like the emission that you assume it has incoming light with different ways of reflecting depending on the property of the surface. So it captures some of the essence of it, basically. Can you see what sort of light source this is from the one? Two of the ones I mentioned on the previous slide.
Point one, the first one.
The one to the left.
Spotlight.
Ah, yeah. Sorry. Yeah, not. Here is how it bounces off surfaces. So these different light types will have how you model the light itself. Now I'm thinking more about the reflection from the object, as I showed here. So we have ambient, diffuse, specular. So two of them are shown here, basically. So which one is which?
Well, the one in the middle is probably specular.
Yes,
First
exactly.
one is ambient.
I think
The
that's
one on the left is ambient.
It's right that the one in the middle is specular.
Yes.
Because as you see, when you see this spark, you will see it, with a little bit of movement back and forth. So it's not entirely reflecting in one direction, but in a little lobe, in certain directions.
The first.
This one is reflecting just in one direction. And this one is basically from the incoming wave, reflecting in all directions.
I think so. That's
So the one on the right
the first one is the ambient because it needs to be.
But remember, ambient doesn't have any direction, so it doesn't depend on the incoming light wave. It's just a
Okay, so
That's
that's the
one.
diffuse.
Yes, it's diffuse, yeah.
I was going to say diffuse.
You say, okay, great. That's nice. So this is diffuse.
Alright.
It's basically, the intensity depends on the incoming light ray, but it will all scatter in all directions, which will make you get this appearance, as you see here. So here light comes in from the right, and you see that that part of the surface is basically reflecting evenly in all directions. As we talked about specular reflections, they will be reflected at certain angles. What is the last one then, to the right? What reflects like that? So if you shine a very sharp beam into it, it basically bounces off completely in one direction. Perfect mirror, yes. Right. So to talk about all of these things, it's very important to consider surface normals, and this is why we also attach this as an attribute to the vertices we have in OpenGL, just like we attach texture coordinates and colors and all those things. Because the normal will basically tell you how sharp a surface is lit depending on how you tilt your surface in space with respect to the light source. So we already seen this here, right? If light comes in this direction and you have the normal there, it will look sharper than if I would have it in at this angle, for example. So it basically follows this equation. But you can also see it in another way. You can say that the normal is pointing towards you, right, from the surface. And in that case, if you view the surface in like that and you have a surface here with a normal vector, then you can also take the dot product. And the fact that that is negative means that you're seeing the front of the surface, exactly. So you can use this to tell that you're actually seeing it from this side. And you can also use this to toss out directions you're not interested in, right? Because in this case, for example, if this is not a transparent surface, what happens behind here you're not interested in. So if this is the normal vector you consider, then the one that is not negative you're not interested in. But it's not that simple in all cases, because, as I said, they can be transparent, and then it matters. Yeah, and also, as you already seen, light intensity is related to the dot product of the normal and the light source. So basically, depending on the angle here, you will get different light intensity. And quite often, you can basically say that this is minus cosine theta, just because you usually you can always normalize your vectors. So once you computed a normal vector to a surface, you can normalize it by just simply saying that my new n tilde is equal to the original n I had divided by its length. Because once you have the normal, you can also compute the length. You have the components of the vector. And you can do that with the incoming light rays as well. And then basically, this product always becomes cosine theta from this volume. So sometimes you will see this inner product or this scalar product just substituted with cosine theta. And then it's a more direct way of seeing it, because you really care about the angle between the normal and the incoming light ray, right? So it's a bit more explicit. Yes, and then the specular refractions also, it doesn't only depend on the incoming ray, but it depends on where you as an observer is located with respect to this one. So for example, if you're staring down here, if this is your eye, then you will not see the specular reflection. If you're sort of looking in if your eye is here, basically you will see some of it, right? Because you're within the area that is reflected from this. I'll go through both diffuse and specular reflections in a bit more detail. Yes, so I already said it's in all directions, and a lot of surfaces in this room can be approximated as diffuse. Like this wall here, this material, all are pretty diffuse. You can try to shine a light on it, and we'll see basically that how much bounces off depends on the angle you have with this flashlight light. But it will not depend on where you're standing in the room what you see. You will see the same light coming to you anyway. And yes, as I already tell, the brightness is then related to cosine theta for this exact reason here. and you, as I also told a bit earlier, if you have a negative dot product and the reflection is visible, if it's not, you basically don't see it, and you can toss it out of your rendering. A little bit more about specular reflections. They're a bit more complicated to deal with, but not that much. Basically, as I said, you will see things. If you're watching this outcoming angles here, you will see it, otherwise you will not. Yeah, and it basically reflects most of the light. That's why it appears bright. It doesn't really have a color, or it does have a color too. That's also one of the problems in color science, to determine how you perceive a surface with specular reflections. It's not so easy always to say what sort of color you do perceive. But there's a little change in the angle and how you model what you see, the width of this outgoing surface here. It's not just cosine theta, but you can model it quite neatly by just taking the power of n, or cosine. Anybody sees why? So by taking cosine theta to the power of n, you can describe the width of this outgoing light. I can give a hint. If n is 1, then you have the maximum. If n is very small, then then this area, which spreads out a little bit smaller and smaller. It's because, of course, cosine is defined between 0 and 1. And when you take the power of number 0 and 1, it gets smaller and smaller the higher the power is, which means that this area shrinks. So this is how it's modeled when we program this, the specular reflections. I'll get back to that in the next lecture. We'll just show how you code this. Then you basically use this one, whatever angle you're interested in, the cosine to the angle. Any questions to this? So let me see. Yeah, we are nearly done. Okay. So that's, yeah, the one thing I haven't talked about is light emission. Both when you model a light source, as well if you model a surface that's, for example, glowing if you heat it up, you will have emission from the surface itself. And that is also quite easy. You can basically, in the simplest way, just add some extra brightness to that surface. If you, for example, want a red glowing surface, you just add some more brightness to it in the color red, basically, and it will appear as it's glowing. Basically, you give it the appearance of being a light source on its own. And then you emit light in all directions from this surface, for example. But when you model the light source itself, you use the same sort of principle. So you have a point that, in one case, we have a light bulb, we have this point basically that radiates in all directions. You may put a sphere around it that sort of colors it in different colors to make it look a bit more like a light bulb of different temperatures, for example. So that was the last part of these 4 things in the Fung model. So basically, just to go back to the Fung model, ambient light, diffuse light, specular light, plus emission gives you this Fung reflection model. So I think that's it for today. It's quite lengthy what continues, so we need another hour. I will get back to this in 1.5 weeks' time, because next week we'll have a lab on Tuesday, and since we cannot stress enough that we should get this assignment 1 going, we will basically concentrate on assignment 1 on Tuesday, so that will be about that. Next Thursday is a skiing day, I think, so there's no lectures put up. And then there will be no lecture, basically. So next week is basically all assignment 1. And next week, I'm not exactly sure how to do it. It may be that following Tuesday we'll have a 1-hour session where we continue this lighting business and start to talk about how we code this thing, this Fung model, with a lab related to it, which you can play around with afterwards. So it's quite nice to have that just afterwards. And then what will be the rest of that week, we will see, depending on what is necessary. But I think we will need 1 more lab and 1 more lecture between now and the deadline of assignment 1 to be able to get enough things to start assignment 2 early in March. So yeah, I will continue this then. So now we can focus on your assignment basically. for now. Any questions?
The book which you have referenced, the Super Bible.
Super Bible, yeah.
Does that book, because I've ordered it and it's coming to me.
Yeah.
Does that include any like references or chapters about lighting?
It does. It has. It's a bit far out. So I far out in the. It's a later chapters because it's about rendering. So it's under more advanced topics. But from 568 to 577 until now, you may read.
Right.
It's not details on what I went through today. It's more about how you code this font. It's about font shading and something called garage shading. I'll get back to that on the next Tuesday, but that you may read for now. And here's more details about all these different rendering methods. If you want to know more details about it, you'll probably not use them that much in this course anyway. And then you have this other for, about light and colors and all that stuff. It's basically other books. So, but the most important part is that you, of course, know how to code this thing and how you make it look nice. But it's always nice to know a little bit around what these things are. So if you're interested, you might read in more details of these things.
Yes.
Okay. Then I think we're done.